Welcome back to QHSE Talks. You know, when a massive industrial catastrophe hits the evening news, like a refinery explosion or a chemical spill, the immediate public reaction is almost always shock.
Oh, absolutely. People just assume these are, freak accidents.
Right, like it's an unpredictable act of nature or something.
Yeah, or just the inevitable cost of complex engineering, like, well, things break.
Exactly. But if you're prepping for your ASP or CSP exam, or you're a safety professional actually running daily operations on the floor, you know the chilling truth there.
You know that disasters rarely come out of nowhere. I mean, they leave a trail of breadcrumbs.
A huge trail.
Yeah.
They are the result of systemic failures that could have been predicted, mapped out, and neutralized months or even years before the spark ever hit the fuel.
Yeah, before anyone even got hurt.
So today's mission on this QHSE Talks is to master ASP 11 Domain 2 Topic 3. We're focusing entirely on applying appropriate hazard and risk analysis methods.
Which is such a massive and critical topic.
It really is. And we are not just going to memorize acronyms here. We're going to look at the diagnostic algorithms you use to dismantle a disaster before it happens.
And, that proactive dismantling is really the core of modern safety engineering.
Right.
We're talking about transitioning from a reactive mindset, like waiting for something to break and then investigating it, to a highly predictive framework.
Getting ahead of the curve.
Exactly. The tools we are covering today, they range from qualitative team brainstorms, like what-if analyses.
Which are super common.
Very common, ranging all the way to highly structured mathematical logic trees like fault tree and event tree analysis.
Oh man, the logic trees, those are heavy.
They are. They're essentially the different diagnostic methodologies you apply depending on the complexity of the system in front of you.
Yeah.
By the end of this discussion, you'll understand not just what these tools are, but the exact mechanisms of how and why they function out in the field.
Okay, but before we get into those really complex methodologies, I want to ground us in the foundational vocabulary.
Good call. You have to start there.
Because ANSI and the safety engineering community, they have incredibly strict definitions for a reason. These aren't just academic terms, right?
No, not at all. They are the legal and operational bedrock of how we assess a workplace.
Yeah, and the biggest trip up I see constantly, both on the exams and in real life, is the conflation of the terms hazard and risk.
Oh, all the time.
Oh.
People use them like they mean the exact same thing.
Right. In casual conversation, sure, people use them interchangeably, but in our field, failing to distinguish between them can completely derail a safety management system.
It absolutely will derail it because, well, you're trying to measure two completely different dimensions of reality.
Tell me more about that. Break down the strict definitions for us.
Okay, so let's look at a hazard first. A hazard is a condition, a set of circumstances, or, an inherent property that has the potential to cause injury, illness, or death.
It's just a state of being.
Exactly. It's the physical presence of a toxic chemical. It's the kinetic energy of a suspended load on a crane.
Or the voltage running through a live wire.
Right. The hazard just is. It exists regardless of whether anyone is around it.
Okay, so it's the potential energy waiting to be released.
Yes, that's a perfect way to put it.
Whereas risk is the statistical calculation applied to that hazard?
Exactly. Risk is the estimate of the combination of the likelihood of a hazardous event occurring and the severity of the resulting injury or illness.
So likelihood plus severity.
Yeah.
Let's unpack this with a real example.
Okay, let's say you have a vat of highly corrosive acid.
Nasty stuff.
Right. The acid is the hazard, and that hazard level does not change. It is inherently corrosive. It's always going to burn you.
The chemical makeup is static.
Yes. But if that vat is just sitting in the middle of a busy factory walkway in an open container, the risk is massive.
Because the likelihood of someone bumping into it or interacting with it is super high.
Exactly. Now, if you take that exact same hazard, the exact same vat of acid, and you seal it inside a double-walled, impact-resistant vault in a restricted access bunker.
You haven't changed the hazard at all. The acid is still just as corrosive.
Right. But you have drastically reduced the risk because the likelihood of human exposure essentially approaches zero.
That makes so much sense. So you can't even begin to mitigate a risk without first identifying the total hazard burden of the system.
Bingo.
I was actually reading through the source materials on this, and That phrase hazard burden, it really stood out to me.
It's a great term.
It sounds like you're calculating the total weight of potential danger an organization is just carrying around every day.
It's a very apt way to describe it. I mean, the hazard burden refers to the complete range, nature, distribution, and significance of the hazards within a given system.
So mapping the entire landscape.
Yeah, mapping the potential energy, the toxic exposures, mechanical dangers, all of it. If you don't know your hazard burden, any risk assessment you do is basically just guessing in the dark.
You're just throwing darts blindfolded.
Pretty much, yeah.
Which brings us to how we get that first light in the dark. Like, let's say we have a brand new project.
Okay, fresh start.
Yeah, maybe an entirely new manufacturing line is being proposed. The blueprints are still just schematics on a screen.
We'd use a preliminary hazard analysis there, a PHA.
Right. It's our first look.
Yeah, the PHA is a primary feature of system safety precisely because it happens so early in the life cycle.
So you're catching things before they even exist physically.
Exactly. Use it to identify and categorize hazards right out of the gate before you've bent a single piece of steel or poured any concrete.
What exactly are you looking at, though, if nothing is built yet?
Well, you're looking at the proposed materials, the general operating environment, and the basic energy sources that will be required.
Ah, okay. So, like, we plan to use highly flammable gas here, so we already know there's a huge fire hazard.
Right. It allows you to design hazards out of the system before they are ever built, like choosing a non-flammable alternative before you've even signed a purchasing contract.
That's incredibly cost-effective, too.
Oh, it saves millions.
But, I mean, a PHA is inherently theoretical, right?
It is. It's all on paper.
Yeah, so once that plant is actually built and the workers are on the floor, the theory collides with reality.
Always. Every single time.
And that's where the job hazard analysis, the JHA, has to take over.
Yes, the JHA is a step-by-step review of the actual operations as they are performed.
But I want to challenge something here that comes up a lot.
Okay, lay it on me.
The literature heavily emphasizes that a JHA must be a worker-oriented analysis.
It does.
Why is that so crucial? Like, why not just rely on the engineers who designed the system to analyze it? They know the mathematical tolerances of the machines better than anyone.
That's a fair question. But it's because the engineer knows how the system should work.
Ah.
The worker, on the other hand, knows how the system actually works under pressure. It's the classic work is imagined versus work is done scenario.
Right, because things never go exactly to plan.
Never. Even a job meticulously designed with safety in mind will develop organic hazards over time. Parts wear down, environmental conditions fluctuate.
And production quotas push people to find workarounds.
Exactly. That's a critical point. The normalization of deviance.
Yeah, like the workers might realize that bypassing a specific safety guard saves them 10 seconds per cycle.
And over time, that dangerous workaround just becomes the standard operating procedure. No one even thinks about it anymore.
Because it's efficient.
Right.
Right.
If you only look at the engineering schematics, you miss that human behavioral element entirely.
The schematics assume perfect human compliance.
Which is a fantasy. A worker-oriented analysis forces the safety professional out of the office and onto the floor.
You actually have to talk to people.
Yes. You have to ask the people turning the wrenches to provide the intelligence. They are the ones who know that a specific machine jams every time the humidity spikes.
Or that a particular tool handle gets super slippery with hydraulic fluid by the end of a 12-hour shift.
Exactly. The workers are closest to the hazard burden. They touch it every day.
It reminds me of trying to understand traffic patterns in a city.
Okay, I like where this is going.
Like, you can look at satellite maps all day long, but if you really want to know where the treacherous intersections and the hidden potholes are...
You ask a taxi driver.
Exactly. You ask the driver who navigates those specific streets for 12 hours a day. They know the reality.
That's a really solid way to visualize it. And, you know, workers often devise their own brilliant, undocumented ways to mitigate hazards just to get the job done safely.
Oh, for sure. Like custom jigs or makeshift shields.
Right. A good JHA captures those worker-led innovations and standardizes them into the formal safety management system.
So you're learning from the floor, not just dictating to it.
Exactly. It feeds into the broader safety case approach. You systematically demonstrate the safety of a facility through risk summation.
Meaning you combine all these individual ground-level risk values from the JHAs to get a comprehensive picture of the system's overall dangers.
You got it. It's bottom-up intelligence.
Okay, so let's say we have established our baseline.
The foundation is set.
Yeah, we've done our PHAs, we've walked the floor, we've done our JHAs with the operators. We know our hazard burden.
Which is huge.
Right. But now we need to anticipate the variables. We know the hazards exist, but how might they interact in unexpected ways?
That's where things get tricky.
Yeah, this requires structured brainstorming, which introduces us to what we call the qualitative questionnaires, what if, and checklist analyses.
Let's start with the what if analysis because its historical context is actually pretty fascinating.
Oh, really? Where did it come from?
It was developed back in the 1960s by the British chemical industry.
Ah, okay. The boom of plastics and petrochemicals.
Exactly. You have to picture the era. Petrochemical plants were scaling up massively. They were dealing with highly volatile substances under extreme pressures and temperatures.
Sounds like a recipe for disaster.
It was. And the industry realized that waiting for something to explode to learn a lesson was no longer economically or morally viable.
Yeah, you can't just blow up a whole town and say, well, lesson learned.
Right. They needed a way to anticipate operational deviations before the plant went critical.
And the method itself, what if, is deceptively informal, isn't it?
Very. It's qualitative and team-based. You gather a cross-functional group in a room.
So like an engineer, an operator, a maintenance tech, maybe a safety pro.
Yep. Get them all around a table, and you systematically throw hypothetical scenarios at the process.
Like, what if the primary cooling pump fails?
Or what if the raw material supplier sends a batch with double the moisture content?
What if there's a total power loss while the reactor is at peak pressure?
Exactly. You are probing the system's resilience. The goal is to identify exposure scenarios by looking at the causes, the consequences, and the existing controls.
To make sure the risk is kept at an acceptable level.
Yes. But I should warn you, here is the major vulnerability of a what-if analysis.
Okay, what is it?
Its effectiveness is entirely bound by the imagination and experience of the people sitting in that room.
Oh, wow. Yeah, that makes sense. If the team suffers from tunnel vision, or if they are simply fatigued,
They might completely fail to ask the one critical what-if question that actually matters.
because you can't mitigate a scenario you haven't even imagined.
Precisely. If no one asks, what if a bird flies into the intake?
Yeah.
You weren't prepared for it.
And this is why relying exclusively on a free-flowing brainstorm is super dangerous in complex operations.
It lacks rigid structure. Human fallibility is a real problem there.
Right. Which is why safety professionals use checklist analysis to counter that.
Exactly. Checklists bring the structure back.
Now, I have to admit something. When I first studied checklist analysis for the ASP exam, it felt almost insultingly simple.
A lot of people feel that way.
Right, because we are dealing with complex thermodynamic processes and multi-million-dollar robotics, and our primary tool is a clipboard with yes and no checkboxes. It feels like something you'd use to close down a fast food restaurant at night.
I know it seems basic, but the simplicity of the checklist is actually its greatest strength, especially in highly complex environments. We'll look at aviation. Pilots use checklists, not because they don't know how to fly the plane. They've trained for thousands of hours.
Right, they know every dial.
But they use checklists because human memory, especially under stress or fatigue, is incredibly unreliable.
That's a great point. Even experts forget things.
A checklist analysis is a systematic evaluation of a process against a comprehensive, pre-established list of parameters and threshold levels.
So it serves as sort of a cognitive anchor.
Exactly. It tethers you to reality.
So you could have a team of brilliant chemical engineers who are so hyper-focused on the theoretical limits of a pressure vessel
that they completely forget to check if the physical emergency relief valve has actually been inspected in the last 5 years.
Yes, the checklist forces systematic observation of the mundane stuff.
It ensures the baseline is never ignored. It forces straightforward, objective responses. Is the machine guard in place? Yes or no?
Is the temperature below the threshold? Yes or no?
Right. But checklists have their own flaw too.
What's that?
They are purely historical.
Ah, because they're based on things we already know.
Exactly. A checklist is written based on past experiences, known regulations, and previous accidents. It cannot anticipate novel, unprecedented failures.
If it hasn't happened before, it's not on the checklist.
Right.
Which perfectly explains why the most robust qualitative approach is actually combining them, the what-if checklist combination method.
Yes. You are essentially covering your blind spots from both directions.
Merging the two creates a highly comprehensive review, right?
It really does. Usually this involves a physical field tour of the operation.
So you walk the floor with both tools.
Yeah. You use the checklist to ensure that all the known established controls and baseline safety parameters are functioning correctly.
You verify the knowns.
And then you use the what-if methodology to explore the spaces between the checklist items.
So you verify the knowns and then aggressively brainstorm the unknowns.
Exactly. It's a very powerful 1-2 punch.
That makes total sense for a moderately complex operation. But what happens when the operation scales to a level where human brainstorming, even supported by a checklist, is just simply insufficient?
You mean when things get really massive?
Yeah. Let's say we're looking at a massive, continuous flow petrochemical refinery. The variables are so intertwined that informal questions just won't catch the cascading failures.
Right. You can't just brainstorm your way out of a continuous chemical reaction.
Exactly. That requires us to move from qualitative brainstorming to rigorous, structured system explorations, like HAZOP.
Yes. HAZOP, which stands for Hazard and Operability Study.
Okay, break that down for us.
It is a formally structured qualitative method used to systematically investigate every single element of a system.
Every single element. That sounds exhausting.
It is. It was designed specifically to find deviations from an intended design. While a what-if analysis is somewhat freeform, a HAZO is rigidly disciplined.
Explain that discipline for me. How does a HAZOP structure the conversation differently than a what-if session?
Okay, so it uses a very specific matrix of 3 things. Nodes, parameters, and guide words.
Nodes, parameters, guide words. Got it.
First, the team breaks a complex system down into manageable, distinct sections called nodes.
How big is a node?
It could be very small. A node might be a single length of pipe between 2 specific valves.
Wow, that granular.
Yes. Then they identify the critical parameter for that specific node. Let's say for that pipe, the parameter is flow.
Okay, so instead of just randomly asking what could go wrong with the flow in this pipe, the team applies a predetermined set of guide words to that parameter.
Exactly. The guide words are universal across the industry. Words like no, more, less, reverse, part of, as well as...
So it's like a formula.
It is. The team methodically pairs the parameter with every single guide word. So for our node, the questions become highly specific and inescapable.
Like, what are the causes and consequences of no flow?
Yes. What about more flow? What about less flow? What about reverse flow?
It's like applying a mathematical grid over the brainstorming process.
That's a perfect way to describe it. It forces the engineering and safety teams to evaluate every permutation of deviation.
Even ones that seem highly unlikely at first glance, right?
Especially those. If they look at reverse flow, they might realize that a simple pressure drop downstream could pull toxic material back into a safe zone.
Which would be catastrophic.
Exactly. And that realization necessitates the installation of a one-way check valve that they never would have thought of during a casual brainstorm.
The structure forces you to discover those hidden vulnerabilities.
It absolutely does. For every deviation, the team documents the cause, the consequence, the existing safeguards, and the required actions.
That sounds incredibly thorough.
It is, which also makes it incredibly time-consuming and resource-intensive. A good HAZOP can take weeks or months.
I can imagine. But for high-hazard continuous processes, it is the gold standard.
Unquestionably.
But, HAZOP is primarily just for continuous processes like fluids, gases, or chemical reactions moving through a pipe system.
Mostly, yes.
What if our hazard burden isn't a continuous flow? What if we are analyzing a discrete mechanical machine made of thousands of individual solid components?
Like an automobile or an airplane.
Right. That requires a different diagnostic tool entirely, which is where FMEA failure mode and effects analysis comes in.
FMEA is a formal process for studying component failures and how they impact overall operational safety.
It's huge in manufacturing, right?
Huge. Manufacturing, automotive, aerospace, they all live and die by FMEA. You were essentially taking a complex machine apart on paper, component by component, and asking how each piece can break.
Let's anchor this with a very tangible example, because for anyone listening who is studying for the ASP exam, you absolutely must understand the logical direction of FMEA.
Yes, this is a major exam concept.
It is an inductive reasoning process. I always have to stop and remind myself of the difference between inductive and deductive.
It's easy to flip them. Inductive reasoning moves from the specific to the general.
Okay, specific to general.
You start at the very bottom, looking at a highly specific granular component, say a single bolt, a specific electrical relay, or a master cylinder.
And you induce or build upward to determine how the failure of that single specific part impacts the general performance of the entire system.
Exactly. Let's use the master cylinder on an automobile braking system. It's a classic textbook example.
Perfect. So we define the scope, And we assemble our cross-functional FMEA team. First step, we identify the failure mode of that specific component.
Right. And the failure mode is simply the manner in which the item fails.
How does it break?
Basically, for a master cylinder, a failure mode could be the internal rubber seals rupturing, or maybe a catastrophic loss of hydraulic fluid through a crack.
Okay. Next, we determine the effects of that failure. What is the consequence if those seals rupture?
The immediate effect is a loss of hydraulic pressure,
Which translates to a total loss of braking power at the wheels.
which means the car cannot stop.
A severe consequence. So then the FMEA requires us to identify how the failure is detected and what safeguards exist, right?
Yes. Detection might be a low fluid warning light popping up on the dashboard, or the operator physically feeling a spongy brake pedal.
And the safeguard.
The safeguard is usually a dual-circuit braking design, meaning if one half of the master cylinder fails, the other half still maintains pressure to at least two wheels.
Preventing a total catastrophic loss of control. It buys you some time.
Exactly. It's a built-in redundancy.
But mapping this out is only half the battle with FMEA. It's really famous for its quantitative scoring system to prioritize these risks.
Ah, yes, the risk priority number, the RPN.
And this is where I want to push back a little on the methodology.
I have a feeling I know where you're going with this.
Because the RPN seems like it introduces a massive amount of human subjectivity into what is supposedly an objective engineering tool.
The RPN calculation is a massive debate point in reliability engineering, and for very good reason.
Let's explain how it works first. To calculate the RPN, the team ranks 3 variables, typically on a scale of 1 to 10.
Right. Severity, occurrence, and detection.
So, severity. How catastrophic is the consequence? Occurrence. How frequently do we expect this failure mode to happen? And detection. How easy is it to detect the failure before it reaches the user or causes harm?
And then you multiply severity, occurrence, and detection together to get the final RPN.
Right, so a 10 for severity, a 10 for occurrence, and a 10 for failure that is impossible to detect gives you a maximum RPN of 1,000.
Which signals an absolute emergency. Do not build this product.
Exactly. But here is my issue with the RPM in the real world. I've heard stories of engineering teams artificially lowering the severity or occurrence scores during the FMEA meeting.
Oh yeah, RPN massaging.
Yes. They do it just to get the RPM below a corporate threshold, simply because fixing the issue would be too expensive or it would delay production.
That is a very real phenomenon. If corporate policy states that any RPN over, say, 100 requires a mandatory multi-million-dollar redesign,
there is immense psychological and organizational pressure on the FMEA team.
massive pressure. They'll argue to rate a severity as a 7 instead of an 8 just to keep the total score at 98.
Oh, it's not that severe. It's just a 7.
Exactly.
Right.
But you have to realize that is a failure of safety culture, not the tool itself.
Okay, fair. But how do you counteract that subjectivity? How do you keep the team honest?
By anchoring the 1 to 10 scales to hard empirical data whenever possible, occurrence shouldn't just be a gut feeling from the senior engineer.
Right, it shouldn't be a guess.
It should be tied to historical failure rates, warranty claims, or accelerated life testing data.
And severity.
Severity should be tied strictly to standardized injury metrics or financial loss brackets. You have to remove the emotional guesswork.
So a 10 always means a fatality, and 8 always means a hospital admission, things like that.
Yes. But you raise a vital point. No mathematical tool can overcome a toxic safety culture. If management wants to cheat the numbers, they will.
That's a sobering reality for a safety professional. But assuming the FMEA is done with integrity, it's an incredible inductive tool. You fix the weak links from the bottom up.
Absolutely.
However, sometimes we need to look at the system from the top down. We need to look at the ultimate nightmare scenario, the explosion, the total plant shutdown, the fatality, and work backward to figure out the exact pathways that could lead us there.
This takes us right into the realm of graphical logic trees, specifically fault tree analysis and event tree analysis.
If FMEA is inductive, fault tree analysis, or FTA, is purely deductive.
Yes. Deductive reasoning moves from the general down to the specific. You start with the overarching disaster, and you deduce the specific component failures that caused it.
The history of FTA is actually fascinating. It wasn't developed for basic workplace safety at all.
No, it wasn't. Where did it come from?
It was originated by H.A. Watson at Bell Telephone Laboratories back in 1962, and they were primarily using it to evaluate the Minuteman Intercontinental Ballistic Missile Launch Control System.
Oh, wow. High stakes.
Right. When you are dealing with nuclear weapons, you can't rely on trial and error. You can't just brainstorm and hope for the best.
Definitely not.
You need a rigorously structured analytical method to prove that an accidental launch is mathematically virtually impossible.
And the brilliance of the FTA is its visual, diagrammatic approach. It's based on Boolean logic.
Yes, the logic gates. It literally looks like an upside-down tree when you draw it out.
You place the primary undesired event at the very top of the page. Let's look at the example of a catastrophic fire in a chemical storeroom.
Okay, so storeroom fire is our top event.
From that top event, the tree branches downward using logic gates, primarily AND gates and OR gates, to map out the intermediate causation steps all the way down to the basic granular events.
Explain how the logic gates dictate the flow of the disaster for us.
Let's map it out. Below the storeroom fire, at the top, we place an AN gate.
Okay, an AND gate.
An AND gate dictates that the event above it will only occur if all the conditions below it occur simultaneously.
So, for the fire to happen, the AND gate connects to two necessary conditions. Let's say combustible material is present and ignition source is present.
Exactly. If you have fuel but no spark, no fire. If you have spark but no fuel, no fire.
The AND gate is essentially a multiplier of safety. It means multiple failures must align perfectly for the disaster to proceed.
Yes. Now let's follow the ignition source branch further down. Below ignition source, we might place an OR gate.
Okay, how does the OR gate change things?
An OR gate means the event above it will occur if any single one of the conditions below it occurs.
So the OR gate below the ignition source branches out into several possibilities, say electrical short circuit or static discharge or open flame from hot work.
Right. Any one of those single basic events is sufficient to trigger the ignition source condition, which then feeds right up into the AND gate.
This Boolean logic creates a literal roadmap for hazard prevention. When a safety engineer looks at a completed fault tree, their goal is to find the most efficient way to break the chain of logic, right?
You look for the cut sets, the specific combinations of events that lead to the top disaster.
If I see that an OR gate leads directly to the top event, I know I have a massive vulnerability because a single point of failure can cause the whole disaster.
Exactly. You want to design the system so that the disaster is protected by multiple AND gates, requiring 3 or 4 independent, simultaneous failures before anything bad happens.
And while drawing the logical pathways is qualitative, FTA becomes an absolute engineering superpower when it becomes quantitative.
When you start adding the math.
Right. If you assign statistical failure probabilities to the basic events at the very bottom of the tree, let's say the probability of a static spark is 0.01 and the probability of a fuel leak is 0.05.
You use Boolean algebra to calculate the exact overall probability of the top event occurring.
Which is just incredible. The computing power available today has completely transformed this. In 1962, Bell Labs engineers were doing this by hand for relatively simple systems.
Must have taken forever.
But today, safety engineering software can calculate a fault tree with tens of thousands of basic events, plugging in real-time reliability data from sensors.
We can calculate the likelihood of a system failure down to microscopic percentages.
Exactly. It allows us to pinpoint exactly where spending $5,000 on a redundant valve will reduce our catastrophic risk by 90%.
It allows for incredibly precise allocation of safety resources. You know exactly where your money does the most good.
But fault tree analysis is always looking backward from the accident.
Right, it's deductive.
What if we have a known specific failure that just occurred and we want to predict all the different ways the scenario could unfold from that single moment? We don't know the end result yet.
That requires event tree analysis or ETA.
This is a vital distinction for the listener. FTA is deductive, mapping backward from a consequence to its causes. ETA is forward-looking, starting with an initiating event and mapping forward to predict the myriad of possible consequences.
Yes. It illustrates mutually exclusive sequences of events. Think of an ETA diagram branching left to right across the page.
Okay, left to right.
On the far left, you have your initiating event. Let's say a high-pressure coolant pipe ruptures in a facility.
That's the initiator. The clock starts there.
The tree then branches out based on the success or failure of the safety systems designed to respond to that rupture. The first branch point. Does the automated pressure drop sensor detect the rupture?
And the tree splits. Up for yes, down for no.
Let's follow the yes path. The sensor works. The next branch point. Do the automated isolation valves successfully close? Again, it splits into yes or no.
If they close, the consequence is a minor, contained spill.
Exactly. But let's follow the no path from the very first sensor. The sensor fails. The system doesn't even know there's a leak.
Uh-oh.
The next branch. Does the secondary containment basin hold the fluid?
By charting every yes and no pathway through the safety layers, the ETA maps out every possible end state, ranging from safe shutdown with minor equipment damage all the way to total facility loss with environmental contamination.
And just like the fall tree, you can assign probabilities to the success or failure of each branch to predict the mathematical likelihood of each consequence.
These logic trees, FTA and ETA, they really are two halves of the same predictive coin.
They are. They're the most advanced ways we can mathematically model the hazard burden of a complex system.
However, there is a hard truth in safety engineering.
Let's hear it.
Despite our best predictive efforts, despite the PHAs, the FMEAs, and the logic trees, the real world is infinitely complex.
It is.
Unforeseen interactions happen. Human error introduces wildcards. Incidents still occur.
You can't predict everything with 100% certainty.
And when the predictive models fail and an incident actually occurs, the posture of the safety professional must instantly shift from prediction to forensic investigation.
Right into detective mode.
Exactly.
Yeah.
How do we ensure we are treating the actual systemic disease and not just slapping a bandage on the most obvious symptom?
Yeah, it brings us to our final operational area, causal analysis techniques, or as most people call it, drilling down to the root cause.
When an incident happens, conducting a root cause analysis is a non-negotiable requirement of any decent safety management system.
Absolutely a non-negotiable. The goal is to systematically identify the underlying factors that contributed to the event so we can prevent recurrence. We have to move past the immediate cause.
Let's start with a highly visual investigative tool, the cause and effect diagram,
Most commonly known as the Fishbone diagram.
or the Ishikawa diagram, named after Dr. Kaoru Ishikawa, who pioneered it for quality management in Japanese shipyards.
The visual structure is really the key to its utility. You draw a long horizontal line across a whiteboard that's the spine of the fish.
Right.
At the far right end, the head of the fish, you define the specific problem or incident, let's say unexpected pump-bearing seizure.
Then you draw diagonal branches coming off the main spine, representing the major categories of potential influencing factors.
In traditional manufacturing, these are often the 4Ms, methods, machines, materials, and measurements.
And usually environment and people are added to make it a comprehensive 6-branch diagram.
Yes. The Fishbone diagram is incredibly useful in the immediate aftermath of an incident because, when an accident happens, data is scarce and theories are flying around wildly. Everyone has an opinion.
Everyone wants to point a finger.
Right. So it forces the investigative team to categorize their hypotheses systematically. If someone thinks the bearing seized because it was installed wrong, you map that under methods.
If someone thinks the bearing itself was defective straight from the factory, you map that under materials.
If someone suspects the vibration sensor failed to warn the operator in time, that goes under measurements.
I've always found the Fishbone diagram excellent for organizing the investigation. It ensures you don't hyper-focus on the operator, the people branch, while completely ignoring the maintenance procedures on the methods branch.
It creates a holistic, unbiased map of potential causes to go investigate.
But to truly drill down into the causality of a specific failure chain, nothing beats the relentless psychological persistence of the 5 whys.
Oh, I love the 5 whys.
Yeah.
It is a remarkably elegant drill-down technique.
Where did it originate?
It was developed by Shigeo Shingo. He was one of the primary architects of the Toyota production system. It's heavily utilized in Six Sigma and lean manufacturing today.
The premise is deceivingly simple, isn't it?
It really is. You state the problem and you ask why it occurred. Then whatever the answer is, you ask why to that answer.
Just keeping asking why.
Yeah, you repeat this successively, typically 5 times, though it could be more or less, until you strip away the layers of symptoms and hit the foundational systemic root cause.
Now, I know some people criticize the 5 whys as being too simplistic, almost like a forensic investigator just playing the role of a stubborn toddler who won't accept the first answer.
Why?
Exactly. But that stubbornness is exactly the point, isn't it?
It absolutely is the point. Because
Right.
human nature and corporate culture in general, they want to find the quickest, easiest explanation for a problem so everyone can just get back to work.
Tie it up in a neat little bow.
Right. And very often, the ostensible reason the first answer you get is just a superficial symptom. And it almost always ends in human error.
Oh, the dreaded human error.
If you stop a human error, you have suffered a catastrophic failure of safety management. You haven't fixed anything. You've just blamed someone.
Let's play this out with a scenario to show how powerful this is. Let's say a worker suffers a serious laceration to their hand while operating a stamping press.
Okay, terrible incident. Let's start the 5 whys.
First, why? Why was the worker's hand lacerated?
Answer: because their hand was in the point of operation when the press cycled.
Okay, if we stop there, the solution is just to write up the worker for a safety violation and tell everyone at the morning meeting to be more careful.
We blame the victim.
Exactly, but we push deeper. Second, why? Why was the worker's hand in the point of operation?
Answer: because the 2-hand safety interlock system had been bypassed.
Whoa. Now the investigation shifts from human clumsiness to intentional procedural deviance.
Things are getting interesting. Third, why? Why was the safety interlock bypassed?
Answer: because the machine frequently jams, and bypassing the interlock is the only way the operator can clear the jam quickly enough to maintain the required production speed.
Now we're hitting operational conflict. Production goals are directly conflicting with safety engineering.
So we asked the fourth why. Why does the machine jam so frequently?
Answer: because the metal blanks being fed into the press are slightly out of tolerance, causing them to stick in the die.
And now we get to the systemic root. Fifth, why? Why are out-of-tolerance metal blanks being used in the first place?
Answer: because the corporate procurement department switched to a cheaper, lower-tier steel supplier last quarter to meet a mandate to cut supply chain costs by 5%. And they did it without consulting the engineering or safety teams on how that material would actually perform in the machines.
Well, wow, that is the magic of the 5 whys right there.
In 5 questions, we completely changed the narrative.
We went from a careless worker put his hand in a machine to disconnected corporate purchasing policy is creating severe physical hazards on the factory floor.
The root cause isn't the worker. It's the siloing of corporate decision-making.
And you can't fix that with a safety poster in the break room.
Not a chance. You fix it by requiring safety approval for all future supply chain changes. You change the system.
And that systemic view of failure is deeply supported by other advanced methodologies mentioned in the exam materials too, right?
Yes, like Morton the Management Oversight and Risk Tree.
That one sounds intense.
It is. MORT is specifically designed to analyze how management's allocation of resources, their policies, and their operational pressures directly contribute to risk. It puts the magnifying glass on leadership.
And there's also Taproot, right?
Yeah. Taproot is a highly structured software and training system that guides investigators past human error. It helps find the exact systemic flaws in training, procedures, or equipment design so that the exact same problem truly cannot recur.
It's just incredible to step back and look at how all these tools interconnect to form an impenetrable safety net.
They really build on each other.
We start by defining our hazard burden with preliminary and job hazard analyses.
Then we use the qualitative brainstorming of what-ifs and checklists to catch the obvious gaps.
Right. And then we apply the rigorous matrix of HAZOP to complex continuous flows.
We use the inductive, bottom-up logic of FMEA to build stronger, more resilient individual components.
And we use the deductive, top-down Boolean logic of fault tree analysis to mathematically map out and prevent ultimate disasters.
And finally, when the net occasionally breaks despite all of that, we use the Fishbone diagram and the 5 whys to stitch it back together stronger than before.
It is a complete, holistic life cycle of risk management.
When you understand these tools, you realize that safety is not an abstract concept or just a matter of luck.
No, not at all.
It is a highly engineered, mathematically supported discipline. Mastering these techniques is the core competency of a modern safety professional.
And for those listening, whether you are prepping for the ASP or just sharpening the saw for your daily practice on the floor, that is the ultimate takeaway from this discussion.
You aren't just learning these definitions to pass a multiple-choice test.
No. You are learning how to see the invisible matrices of failure operating in the background of your facility. You are learning how to look at a system and mathematically prove where it's going to break before a single drop of blood is spilled.
You are shifting your entire organizational culture from a reactive posture, where safety is just the department that shows up to investigate accidents, to a proactive posture,
where safety is engineered into the very DNA of the operation, from the earliest blueprints to the daily purchasing decisions.
That's the goal.
As we wrap up this QHSE talks, I want to leave you with a final thought to ponder. We discuss how a fault tree analysis, or an FMEA, can mathematically reveal that a single component failure, an OR gate, can cause a catastrophic event.
A single point of failure.
Right. But I want you to think beyond the engineering schematic for a second. If a single point of failure exists in a massive industrial system, how does the psychology of the organization, the management oversight, play into allowing that single point of failure to remain unaddressed?
That's a profound question.
If everyone knows the RPN number is high, why does the culture allow it to persist? Tomorrow, when you walk onto the floor, I want you to look around. Ask yourself, which of these diagnostic tools would I deploy first to uncover the hidden hazards disguised as normal operations right in front of me? The methodologies are in your hands. The future is yours to predict. We'll catch you on the next episode of QHSE Talks.